I say today is going to be for n by n systems, but for your calculations in the exams, 2 by 2 will be good enough. So our system looks like that. Notice I'm talking today about the homogeneous system, not the inhomogeneous system. So homogeneous. And we have so far two basic methods of solving it. The first one, on which we spent the most time, is the method of where you calculate the eigenvalues of the matrix, the eigenvectors, and put them together to make the general solution. So eigenvalues, e-vectors, and so on. The second method, which I gave you last time, I call the Royal Road, simply calculates the matrix e to the at and says that the solution is e to the at times x0, the initial condition. That's very elegant. The only problem is that to calculate the matrix e to the at, although sometimes you can do it by its definition as an infinite series, most of the time the only way to calculate the matrix e to the at is by using the fundamental matrix. In other words, the normal way of doing it is you have to calculate it as the fundamental matrix time normalized at 0. So as I explained at the end of last time, and you've practiced in the recitations, you have to find the fundamental matrix, which of course you have to do by eigenvalues and eigenvectors, and then you multiply it by its value at 0 inverse. And that, by magic, turns out to be the same as the exponential matrix. But of course, there has been no gain in simplicity or no gain in ease of calculation. The only difference is that the language has been changed. Now, today is going to be devoted to yet another method which saves no work at all, and it only amounts to a change of language. The only reason I give it to you is because I've been begged by various engineering departments to do so, because that is the language they use. In other words, each person who solves systems, some like to use fundamental matrices, some just calculate, some immediately convert the system by elimination into a single higher order equation because they're more comfortable with that. Some talk, especially if they're writing papers, they talk exponential matrices. But there are a certain number of engineers and scientists who talk decoupling. Express the problem and the answer in terms of decoupling, and that's therefore what I have to explain to you today. So the third method, today's method, I stress it's no more than a change. It's really no more than a change of language, and I feel a little guilty about the whole business because it's instead of going more deeply into studying these equations, what I'm doing is it's like giving a language course, and I'm teaching you how to say hello and goodbye in French, German, Spanish, Italian. It's not going very deeply into any of those languages, but you're going into the outside world where people will speak these things. So here's an introduction to the language of decoupling, in which some people is the exclusive language in which they talk about systems. Now, I think the best way to, well, in a general way, what you try to do is as follows. You try to introduce new variables. You make a change of variables. I'm going to do it just 2 by 2 just to save a lot of writing out. And so let's call the change. It's going to be a linear change of variables because we're interested in linear systems. So the problem is to find u and v such that something wonderful happens, such that when you make the change of variables to express this system in terms of u and v, it becomes decoupled. And that means the system turns into a system which looks like u prime equals k1 times u and v prime equals k2 times v. Such a system is called decoupled. Why? Well, in a system, a normal system is called coupled. Let's write it out what it would be. It would look like, oh, I can't use a, let's not write it out. You know what it looks like. This is decoupled because it's not really a system at all. It's just two first-order equations sitting side by side and having nothing whatever to do with each other. This is two problems from the first day of the term. It is not one problem from the next to last day of the term, in other words. To solve this, all you say is u is equal to a constant, some constant times e to the k1t, and v equals another constant times e to the k2t. Coupled means that the x and y occur in both equations on the right-hand side, and therefore you cannot solve separately for x and y. You must solve together for both of them. Here I can solve separately for u and v, and therefore the system has been decoupled. Now obviously if you can do that, it's an enormous advantage, not just to the ease of solution, because you can write down the solution immediately, but because something physical must be going on there. There must be some insight. There ought to be some physical reason for these new variables. Now, that's what I plan to start with. So my plan for the lecture is, first, to work out in some detail a specific example where the decoupling is done, to show how that leads to the solution, and then we'll go back and see how to do it in general, because you will see that as I do the decoupling in this particular example, that particular method, though it's suggestive, it will not work in general. I need a more general method. But let's first go to the example. It's a slight modification of one you should have done in recitation. I don't think I worked one of these in the lecture, but to describe it, I have to draw two views of it to make sure you know exactly what I'm talking about. So it's our old, sometimes it's called an ice cube, the two-compartment ice cube tray problem. You know, you fill an ice, it's a very old-fashioned type of ice cube tray, not a modern one, which is all plastic and where there's no leaking from one compartment to another. But the old kind of ice cube tray, you know, there were compartments, and these were metal separators, and you leveled the liquid because it could leak through the bottom. They didn't go right to the bottom. If you don't know what I'm talking about, it makes no difference. So I'm going to so this is the side view. This is meant to be twice as long, but to make it quite clear, I'll draw the top view of this thing. You have to imagine this is a rectangle, all the sides are parallel and everything. This is 1 and this is 2. All I'm trying to say is that the cross-sectional area of these two chambers, this one has twice the cross-sectional area of this one. So I'll write a 2 here and I'll write a 1 there. Of course, it's this hole here through which everything leaks. I'm going to let x be the height of this liquid, the water here, and y the height of the water in that chamber. Obviously, as time goes by, they both reach the same height because of somebody's law. Now, what's the system of differential equations which controls this? Well, the essential thing is the flow rate through here. So that flow rate through the hole in units, let's say in liters per second, just so you understand, I'm talking about the volume of liquid that goes through in a, I'm not talking about the velocity. That's proportional to the area of the hole, the cross-section, the size of the hole. So the area of the hole, the cross-sectional area, right? And it's also times the velocity of the flow. But the velocity of the flow depends upon the pressure difference. And that pressure difference depends upon the difference in heights. All those are various people's laws. So times the height difference. And of course, you have to get the sign right. So I just point out the height difference is proportional to the pressure at the hole. And it's that pressure at the hole which determines the velocity with which the fluid flows through. So where does this all produce our equations? Well, x prime is equal to, therefore, some constant depending on the area of the hole and this constant of proportionality with the pressure and the units and everything else, times the pressure difference I'm talking about. Well, if fluid is going to flow in this direction, that must mean the height, the y height, is higher than the x height. So it should be, to make x prime positive, it should be y minus x here. Now, the y prime is different because, again, the rate of fluid flow is determined. This time it will be x minus, if y prime is positive, if this is rising as it will be in this case, it's because the fluid is flowing in that direction. It's because x is higher than y. So this should be the same constant, x minus y. But notice that that will not, that's the rate at which the right-hand side is the rate at which fluid is flowing into this tank. That is not the rate at which y is changing. It's the rate at which 2y is changing. Why isn't there a constant here? There is. It's 1. That's the one that's this one cross-section. So the area here is 1, and the area, cross-sectional area here is 2. And that's the reason for the 1 here and the 2 here. Because we're interested in the amount by which the fluid is, the rate at which fluid is being added to this, which is only related to the height, the rate at which the height is rising, if you take into account the cross-sectional area. So there's the system. In order to use nothing but integers here, I'm going to take c equal to 2 so I don't have to put in halves. So the final system is x prime equals minus 2x. You got to write them in the right order, right? And y prime equals, the 2's cancel because c is 2. So now it's x minus y. So there's our system, and now the problem is I want to solve it by decoupling it. I want, in other words, to find new variables, u and v, which are better, more natural to the problem than the x and y, that are so natural to the problem that the system, the new system, will just consist of the two side-by-side equations instead of the single equation. So the question is, what should u and v be? Now, the difference between what I'm going to do now and what I'm going to do later in the period is, later in the period, I'll give you a systematic way of finding what u and v should be. Now, we're going to psych it out. Psych out what they should be in the way in which people who solve systems often do. I'm going to use the fact this is not just an abstract system of equations. It comes from some physical problem. And I ask, is there some system of variables which somehow go more deeply into the structure of this, what's going on here, than the naive variables which simply tell me how high the two tank levels are? That's the obvious thing I can see, but are there some variables which go more deeply? Now, one of them is obvious, sort of obvious, and suggested both by the form of the equation and by this. It's simply the difference in heights is in some ways a more natural variable because that's directly related to the pressure difference, which is directly related to the velocity of flow. They will differ by just constant. So I'm going to call that the second variable, the difference in heights, let's call it. So that's x minus y. That's a very natural variable for the problem. The question is, what should the other one be? Now you sort of stare at that a while until it occurs to you that something is constant. What's constant in this problem? Well, the tank is sitting there. That's constant. But what thing which might be a variable is clearly a constant, must be a constant? It would be the total amount of water in the two tanks. These things vary, but the total amount of water stays the same because it's a homogeneous problem. No water is coming in from the outside and none is leaving the tanks through a little hole. Okay, what's the expression for the total amount of water in the tanks? X plus 2y. Therefore, that's a natural variable also. It's independent of this one. It's not a simple multiple of it. It's a really different variable. So this represents the total amount of, this variable represents the total amount of water, of liquid in the two tanks. This represents the pressure up to a constant factor. It's proportional to the pressure at the hole. Okay, now what I'm going to do is say, okay, this is my change of variables, and now let's plug in and see if what happens to the system when I plug in these two variables. Now, how do I do that? Well, so I want to substitute, get the new system. The new system, or rather the old system, but in terms of what makes it new is in terms of U and V. What will that be? Well, U prime is x prime plus 2y prime. But I know what x prime plus 2y prime is because I can calculate it from this. What will it be? X prime plus 2y prime is negative 2x plus twice y prime. So it's plus 2x, that's 0. And how about these two? 2y minus twice this, because I want this plus twice that. So it's 2y minus 2y, again 0. The right-hand side becomes 0 after I calculate x prime plus 2y. So that is 0. Which is, of course, clear. Now, that makes sense, of course, because since the total amount is constant, U prime, that says that U prime is 0. Okay, what's V prime? V prime, well, that's x prime minus y prime. What's that? Well, once again, we have to calculate. It's x prime minus y prime is minus 2x minus x. That's minus 3x. And 2y minus negative y, that makes 3y, plus 3y. All right, what's the system? The system is U prime equals 0, and V prime equals minus 3 times x minus y, but x minus y is V. In other words, these new two variables decouple the system. And we got them, as scientists often do, by physical considerations. These variables go more deeply into what's going on in that system of two tanks than simply the two heights, which are too obvious as variables. All right, what's the solution? Well, the solution is U equals a constant, and V prime, and V is equal to, well, the solution to this equation is some constant, a different arbitrary constant from that one. These are side-by-side equations, which have nothing whatever to do with each other, remember, times e to the minus 3t. Now, there are two options. Either one leaves the solution in terms of those new variables, saying they're more natural to the problem, but sometimes, of course, one wants the answer in terms of the old ones. If you do that, then you have to solve back. In order to save a little time, since this is purely linear algebra, I'm going to write what the, instead of, taking 2 minutes to actually do the calculation in front of you, I'll just write out what the answer is. So to express in terms of U and X and Y, so in other words, this is a perfectly good way to leave the answer if you're allowed to do it. But if somebody says they want the answer in terms of x and y, well, you have to give them what they're paying for. So in terms of x and y, you have first to solve those equations backwards for x and y in terms of u and v, in which case you will get x equals 1/3 u plus 2v. Use the inverse matrix or just do elimination, whatever you usually like to do. And the other one will be 1/3 u minus v. And then if you then turn these, substitute in, you'll see what you'll get is 1/3 of C1. C1, U is, U is C1. Plus so, all right, C1 plus 2C2 e to the negative 3t. And this is 1/3, what is it, C1 minus C2 e to the minus 3t. And so the final solution is, in terms of the way we usually write out the answer, then x will be what? Well, it will be 1/3 C1 times the eigenvector 1, 1, plus 1/3 times C2 times the eigenvector 2, negative 1, times e to the minus 3t. So that's the solution written out in terms of x and y, either as a vector in the usual way or in terms separately in terms of x and y. But notice, in order to do that, you have to have the equations, these backwards equations. In other words, I need the equations in that form. I need the equations because they tell me what the new variables are. But I also have to have the equations the other way in order to get the solution in terms of x and y finally. Okay. That was all an example. For the rest of the period, I'd like to show you the general method of doing the same thing, which does not depend upon being clever about the choice of the new variables. And then at the very end of the period, I'll apply the general method to this problem to see whether we get the same answer or not. So what's the general method? Our problem is to decouple. Now, the first thing is, you can't always decouple. You must, to decouple, the eigenvalues must all be real. Must all be real and non-defective. In other words, if they are repeated, they must be complete. You must have enough independent eigenvectors. So they must be real and complete. If repeated, they must be complete. They must not be defective. As I told you at the time when we studied complete and incomplete, the most common case in which this occurs is when the matrix is symmetric. If the matrix is real and symmetric, then you can always decouple the system. That's a very important theorem, because particularly since many of the problems, equilibrium problems, normally lead to symmetric matrices, and they're solved by decoupling. Okay. So what are we looking for? So we're assuming this, and we need it. In general, otherwise, you cannot decouple if you have complex eigenvalues, and you cannot decouple if you have defective eigenvalues. Well, what are we looking for? We're looking for new variables. UV equals A1, B1, A2, B2 times the XY. And the question is, this matrix is called D. It's called the decoupling matrix, and it's what we're looking for. How do I choose those new variables u and v when I don't have any physical considerations to guide me as I did before? Now, the key is to look instead at what you're going to need. Remember, we're changing variables, and we're changing, I told you from the beginning, first days of the term, when you change variables, look at what you're going to need to substitute in to make the change of variables. Don't just start writing equations. What we're going to need to plug into that system and change it to the UV coordinates is not u and v in terms of x and y. What we need is x and y in terms of u and v to do the substitution. So what we need is the inverse of this. So I'm going to write that. So this is in order to do the substitution, what we need is x, y. Oops, I shouldn't have called these. Let's call them prime. Okay? The real A1 and A2 is going to be, let's call these A1, because these are going to be much more important to the problem than the other ones. Okay, I should call this matrix D inverse. That would be a sensible thing to call it. Instead, since this is the important matrix, this is the one we're going to need to do the substitution, I'm going to give it another letter instead, and the letter that comes after D is E. Now, E is an excellent choice because it's also the first letter of the word eigenvector. And the point is, the matrix E which is going to work is the matrix whose columns are the two eigenvectors. The columns are the two eigenvectors. Now, even if you didn't know anything, that would be practically the only reasonable choice anybody could make. What are we looking for? We're looking for to make a linear change of variables like this really means to pick new I and j vectors. You know, from the first days of 1802. What you want is a new coordinate system in the plane, and the coordinate system in the plane is determined as soon as you tell me what the new I is and what the new j is in the new system. So what you have to establish a linear change of coordinates amounts to picking two new vectors which are going to play the role of I and j instead of the old I, and the old j. Okay, so pick two vectors which somehow are important to this matrix. Well, there are only two, the eigenvectors. What else could they possibly be? So the only thing to try, now what's the relation? I say that with this, this automatically makes, what happens is, I say that alpha 1 corresponds, and alpha 2, these are vectors in the xy system. Well, if I change the coordinates to u and v in the uv system, they will correspond to the vectors 1, 0. In other words, what the vector that we would normally call I in the UV system, and this one will correspond to the vector 0, 1. Now, if you don't believe that, I'll calculate it for you. It's very easy the calculation is trivial. Look, what have we got? xy equals. So xy equals a1, b1, a2, b2. This is the vector, the column vector alpha 1, and this is the column vector alpha 2. Okay, now, here is u and v. Okay, suppose I make u and v equal to 1, 0. What happens to x and y? You matrix multiply. 1, 0. 1, so a1 plus 0. b1 plus 0. It corresponds to the column vector a1, b1. And in the same way, 0, 1 corresponds to a2, b2. just by matrix multiplication. And that shows this thing, that these correspond. So in the UV system, the two eigenvectors are now called I and J. Well, that looks very promising, but we still now, the program now is to do the substitution, to substitute into the system x prime equals ax, and see if it's decoupled in the UV coordinates. Now, I don't dare let you do this by yourself because you'll run into trouble, and nothing's going to happen. You'll just get a mess. You'll say, hey, I must be missing something, and that's because you are missing something. What you're missing, and this is a good occasion to tell you, is that in general, 3/4 of the civilized world does not introduce eigenvalues and eigenvectors the way you learned them in 1803. They use a different definition, which is identical. I mean, it's not, it's equivalent. It leads to the concept is the same, but it looks a little different. Our definition is what? Well, what's an eigenvalue and an eigenvector? The basic thing is this equation. What's this? This is a 2x2 matrix, right? This is a column vector with two entries. The product is has to be a column vector with two entries, but both entries are supposed to be 0, so I'll write it this way. So this way first defines what an eigenvalue is. It's something which makes the determinant 0. And then it defines what an eigenvector is. It's then a solution to the system that you can get because the determinant is 0. Now, that's not what most people do. What most people do is the following. They write this equation differently by having something on both sides. Using the distributive law, what goes on the left side is A alpha 1. What is that? That is a column vector with two entries. What goes on the right? Well, lambda 1 times the identity times alpha 1. Now, the identity matrix times anything just reproduces what was there. So there's no difference between writing the identity times alpha 1 and just alpha 1 all by itself. So that's what I'm going to do. This is the definition of eigenvalue and eigenvector that all the other people use. Most linear algebra books use this definition. Most books use a different approach, and they say, here is an eigenvalue and an eigenvector, and it requires them to define them in the opposite order. First, what alpha 1 is, and then what lambda 1 is. See, I don't have any determinant now. So what's the definition? The definition, and they like it because it has a certain geometric flavor which this one lacks entirely. This is good for solving differential equations, which is why we're using it in 1803, but this has a certain geometric content. This way thinks of A as a linear transformation of the plane, a shearing of the plane. You take the plane and you do something to it, or you like that, or you squish it like that, or you rotate it. That's okay too. And the question it asks is, the matrix defines a linear transformation of the plane. Every vector goes to another vector. Is there a vector which is taken by this linear transformation and just left alone or stretched, is kept in the same direction but stretched? Or maybe its direction is reversed and it's stretched, or it's shrunk. But in general, if there are real eigenvalues, there will be such vectors which are just left in the same direction but just stretched or shrunk. And what is the lambda? The lambda then is the amount by which they're stretched or shrunk, the factor. So this way, first we have to find the vector which is left unchanged, and then essentially unchanged, and then we have to, then the number here that goes with it is the stretching factor or the shrinking factor. But the end result is the pair, alpha 1 and lambda 1, regardless of which order you find them, satisfy the same equation. Now, a consequence of this definition we're going to need in the calculation that I'm going to do in just a moment. So let me calculate that out. What I want to do is calculate the alpha A, the matrix A times E. I'm going to need to calculate that. Now, what is that? Well, remember, E is the matrix whose columns are the eigenvectors. So that is the matrix alpha 1, alpha 2. Now, what's this? Well, in both Friday's lecture and Monday's lecture, I use the fact that if you do a multiplication like that, it's the same thing as doing the multiplication A alpha 1 and putting it in the first column, and then A alpha 2 is the column vector that goes to the second column. But what's this? This is lambda 1, alpha 1. And this is lambda 2, alpha 2 by the calculation, by this other definition of eigenvalue and eigenvector. And what's this? Can I write this in terms of matrices? Yes, indeed, I can. This is the matrix lambda, this is the matrix alpha 1, alpha 2 times this matrix lambda 1, lambda 2, 0, 0. Check it out. Lambda 1 plus 0, lambda 1 times this thing plus 0. The first entry is exactly that. In the same way, the second column, doing the same calculation, is exactly this. So what's that? That's E times this matrix lambda 1, 0, 0, lambda 2. Okay, we're almost finished now. So now we can carry out our work. We're going to substitute, do the substitution. So I start with the system. Remember where we are. I'm starting with this system. I'm going to make the substitution X is equal to this matrix E, whose columns are the eigenvectors, and that's going to be, I'm introducing, in other words, new variables, U and V, according to that thing. Did I ever say U? So U is the column vector. Sorry, U is the column vector, U and V. And X, as usual, is the column vector X and Y. So I'm going to plug it in. Okay, let's plug in. So what do I get? I take the derivative. So E is a constant matrix, so that makes E times U prime is equal to A times X is E times U again. And now at this point you would be stuck, except I calculated for you A times E is E times that funny matrix, diagonal matrix of the lambdas. So this is E times that funny matrix of the lambdas, the eigenvalues, and still the U at the end of it. So where are we? E times U prime equals E times this thing. Well, multiply both sides by E inverse, and you can cancel them out. And so the end result is that after you've made the substitution in terms of the new variables U, what you get is U prime equals lambda 1, lambda 2, 0, 0 times U. Let's write that out in terms of a system. So this is UV. What does it say? UV prime is equal to, well, this is UV here, so it's lambda 1 times U plus 0 times V. And the other one is V prime equals 0 times U plus lambda 2 times V. We are decoupled. In just one sentence, in other words, you would say, in other words, if you were reading a book that sort of assumed you knew what was going on, all it would say is, as usual, that's to make you feel bad, or as is well known, to make you feel even worse. the system is decoupled by choosing as the new basis for the system the eigenvectors of the matrix, and in terms of the resulting new coordinates, the decoupled system will be the following, where the constants are the eigenvalues. And so the solution will be U equals C1 times e to the lambda 1t, and V is equal to C2 times e to the lambda 2t. Of course, if you want it back in terms now of x and y, you'll have to go back to here, to these equations, and then plug in for u and v what they are, and then you'll get the answer in terms of x and y. Okay, we have just enough time to actually carry out this little program. It takes a lot longer to derive than it does actually to do. So let's do it for this system that we were talking about before. This can go down. Okay, so decouple the system. xy prime equals, the matrix is -2, 2, 1, -1. Okay, what do I do? Well, I first have to calculate the eigenvalues and the eigenvectors. So the EVs and EVs. Okay, the characteristic equation is lambda squared. The trace is -3, but you have to change the sign. The determinant is 2 minus 2, so that's 0. So there is no constant term here. It's 0. That's the characteristic equation. The roots are obviously lambda equals 0, lambda equals -3. And what are the eigenvalues? What are the eigenvectors that go with that? With lambda equals 0 goes the eigenvector -2. Well, I subtract 0 here, so the equation I have to solve is -2a1 plus, I'm not going to write 2a2, which is what you've been writing up till now. The reason is because I ran into trouble with the notation, and I had to use as the eigenvector not a1, a2, but a1, b1. So it should be a b1 here, not the a2 that you're used to. The solution, therefore, is alpha 1 equals 1, 1. And for lambda equals -3, the corresponding eigenvector this time will be. Now I have to subtract -3 from here. So -2 minus -3 makes 1. So that's a1 plus 2b1 equals 0. So a logical choice for the eigenvector here, the second eigenvector would be make b1 equal to 1, let's say, and then a1 will be -2. Okay, now what do we have to do? Now what we want is the matrix E. The matrix E is the matrix of eigenvectors. So it is the matrix 1, 1, -2, 1. The next thing we want is what the new variables u and v are. For that we will need E inverse. How do you calculate the inverse of a 2 by 2 matrix? You switch the two diagonal elements, which doesn't, okay, there I've switched them. And you leave the other two where they are, but you change their sign. So it's 2 up here and -1 there. Maybe I should make this one purple and then that one purple to indicate that I've switched them. Oh, I'm not done yet. I have to divide by the determinant. What's the determinant? It's 1 minus -2, which is 3. So I have to divide by 3. So I multiply everything here by 1/3. Okay, and what's the decoupled system? So the decoupled system is, so the new variables are u equals 1/3. So right, it's u. So in other words, the new variables are given by d. So it's uv equals 1, 2, negative 1, 1 times 1/3 times xy. That's the expression for, I've covered it up now, but that's u of v in terms of x and y. It's this matrix D, the decoupling matrix, which is the one that's used. And that gives this system u equals 1/3 of x plus 2y on top. And what's the v entry? V is 1/3 of minus x plus y. Now, are those the same variables that I used before? Oh. Yes. The top one, this is my new and better u, the one I got by just blindly following the method instead of looking for physical things with physical meaning. How does it? It differs from the old one just by a constant factor. Now, that doesn't have any effect on the resulting equation because if the old one is u prime equals 0, the new one is 1/3 u prime equals 0. It's still the same equation, in other words. And how about this one? This one differs from the other one by the factor minus 1/3. If I multiply that v through by minus 1/3, I get this v. And therefore, that too does not affect the second equation. I simply multiply both sides by minus 1/3. So the new v still satisfies the equation minus 3 times v.